Hey, hi everybody. My name is Kyle Fogarty. I'm part of the AgriFoRwARDS CDT, and I'm very pleased to be joining you today to talk about uncertainty quantification. In particular, we're going to look at Monte Carlo methods as part of the Computational Toolkit seminar series. Okay, so in this seminar, we're going to focus on Monte Carlo estimators, and my talk is going to be given over 2 weeks. So this week we'll focus on Monte Carlo estimators, which will then form the building block for a technique that we'll discuss next week called random walk metropolis Hastings algorithm. And that's really a key algorithm in being able to take a stochastic model that we may have, and we may have some observations and inferring distributions over parameters of that model, which is something that we often really want to do in science and engineering. So in this talk, all we're going to do is assume that you're comfortable with the basic ideas of probability. If you don't feel so comfortable with them, then underneath this video there'll be linked some resources that you can have a look at to sort of brush up on the ideas of probability theory. Okay, so we're going to begin with the idea of a random variable. So what do we mean by a random variable? So a random variable, usually denoted by an uppercase letter X, is a value chosen by a stochastic process, so a process that's random. So the random variable can really be seen mathematically as a function, and it draws elements from the sample space of a probability space, which we denote by this uppercase omega. And so the random variable can either be continuous or discrete. And a key point about a random variable is that if you apply a function to it, then the output of that function will also be a random variable. And this will become quite useful later when we're discussing Monte Carlo methods. So perhaps to make that idea a little more concrete of what a random variable is, we could take a simple example of rolling a dice. So the sample space of rolling a dice is 1, 2, 3, 4, 5, and 6. They're the faces of the die. And we could construct a random variable in it whatever way we like. So in this case, I've chosen the random variable to take the value 1 if omega is even, and 0 if omega is odd. And once we've constructed our random variable, so the thing that takes the random process and assigns values to it, we can then ask questions about the probability of these events happening. So what's the probability that the dice roll will be even, so equaling 1, well, that'll be 3 events out of the total 6 of the state space, so a half, and likewise for it being odd, 3 events out of the total state space of 6, so a half. Okay, so that was quite a simple example to introduce random variables. Once we have the idea of a random variable and this idea that we can talk about probability of events of different things happening, then it's helpful to introduce the idea of a probability density function. So we're now only going to really talk about continuous random variables. We're not going to bother too much with discrete ones. And a probability density function, denoted here by pi of x, where x is the random variable that we're discussing, of a continuous random variable integrated over an interval. In this case, we're talking about a real valued random variable. So on the interval a to b, gives us the probability that the outcome of x will be in the interval a to b. So in other words, the probability that the random variable lies in this interval is equal to the integral over a to b of the probability density function, pi of x. So this, in some sense, really encodes how density, or the distribution of that probability mass, is associated with the space that it lives in. Okay, so some common probability density functions that we will come across, certainly this week and next week, is the uniform distribution. So that is everywhere within this interval a to b has an equal likelihood, equal probability of being chosen, and so it's simply the difference between 1 over the difference between a and b, and then we have an indicator function, which just means that it's times by 1 inside the interval and 0 everywhere else. And then there's also the Gaussian normal distribution, which I'm sure most people will come across. So this is defined by its mean and its variance, and it has the usual sort of bell-shaped curve. So if we take a quick look at normal distribution, there's this good applet available, so we can set the mean and the standard deviation of something, of a sort of a normal distribution, and then we can query sort of do the integral. So if we say what's the probability that x is less than, let's say, 3, well, then we can see exactly what we mean by performing the integral. So that means it's the shaded region from, in the case of a normal distribution, which is defined on the real line, minus infinity to 3, which is equal to 0.84134. Okay, so when we query what a probability of a random variable is, that's equivalent to performing an integral and looking for the area underneath the curve in some sense. Okay, so once we have the idea of a probability density function and a distribution of a random variable, then we can introduce the idea of looking at its mean or its expectation. So the mean, or otherwise known as its expectation of a random variable, is one of the summary statistics which really starts to describe what the distribution looks like, and it's a generalized weighted average. And so the general formula for an expectation of a random variable, let's say x, is equal to the integral over the region in which x is defined of the product of x itself times by the probability distribution of x. And so another important fact which we mentioned earlier was that if you have a function of a random variable, then that function itself becomes a random variable itself. And so we can quite easily take expectations of functions of random variables by just computing the product of the function and the probability distribution. And this fact will become really important later when we're talking about approximating integrals of real functions using this Monte Carlo method. Okay, so let's have a quick look at perhaps how we can take an expectation of the uniform distribution, which we mentioned a few minutes ago. So this is the sort of formula for taking an expectation. So if we plug in our probability distribution, remember it's 1 over a minus b times by an indicator function. So remember here that a and b are just define the interval on which we're talking about the uniform distribution. So it could be 0, 1, it could be 0, 100, it could be anything on the real line where we want to define this uniform distribution. Okay, so we have the indicator function, and what we can do is, because the indicator function means that the only returns 1 in the interval a to b and 0 everywhere else, well, that's equivalent to replacing the integral over the entire real line just between a and b. And once we have that, then we can perform usual integration, so increase the power by 1 of x divided by the new power, and we find a closed form solution for the expectation of x, which, as we discussed, this gives you the mean, or sort of where the center of the distribution lies. Okay, so once we have the expectation or the mean, it's usual to talk about also the variance of a distribution, which is the second moment, and it discusses the spread of that distribution. So the variance is given by this equation, so it's the random variable minus its mean squared, and then take the expectation of that. So more generally, once we've got the first moment and the second moment, we can talk about the nth moment of a distribution. So that's generalized by this form. So the first moment giving the sort of center of the distribution, the second moment the variance given the spread, the third moment gives some notion of how the distribution is skewed, either one way or the other, And we can go higher and higher moments and keep on describing the distribution with these sort of summary statistics. Let's now discuss Monte Carlo estimators. So what about if this expectation or this integral is too complex for us to be able to compute? So we can't use traditional quadrature approaches to this, or what about, even worse, if we don't have access to the actual random variable? What about if it's not a closed form random variable? But, and key to the Monte Carlo estimator is, what if we can produce samples of that random variable? What if we have observations of a system where it's a stochastic process and we can generate samples in some way of that random process? Well, then what we can do is we can use a Monte Carlo estimator. And so the idea of a Monte Carlo estimator is it's based on the law of large numbers, which is sort of out of the scope of this talk, but means that we can prove that for a sequence of independent and identically distributed samples from a distribution pi, that the expectation of a random variable, so pi is the distribution associated with the random variable x, is equal to the infinite sum of the function evaluated with its samples. Okay, well, that's not particularly helpful because there's an infinite sum there, but the Monte Carlo estimator allows us to truncate that, and of course we'll induce some sort of error, which we refer to as Monte Carlo error, but we can actually approximate this expectation then as a finite sum of independently identically distributed samples from this distribution. Okay, so that's the whole idea of Monte Carlo estimators, and in a few moments time we'll take a look at how we can implement something like this in Python. But before we do, we could then look at Monte Carlo integration, which is sort of just a little bit of an extension of Monte Carlo estimators, or an application of Monte Carlo estimators to integration of real functions. So let's suppose we want to integrate or evaluate this integral of a real function f of x between the interval a to b. Well, then we can say that this is equivalent to this expression here, where we're saying f of x and then we're just times by 1 because b minus a divided by b minus a is 1. But if we actually notice that this is equivalent to b minus a times by, well, what is this? This is the definition of the function, the expectation of the function f of x with a uniform distribution. So if we say here that the pi of x is a uniform distribution on the interval a to b, then what we have here is the expectation of that. And so what that means is we can actually approximate this integral, the integral of a to b of f of x, by using a Monte Carlo estimator that we just introduced a moment ago, where we produce independent and identically distributed samples, SI, on the uniform distribution of a to b. Okay. Now, the idea of Monte Carlo integration in a univariate sense, so when we have a single variable, is not the best, but because often quadrature approaches where we just discretize space and sort of use the discretized grid to evaluate the integral will work a lot better. But the power of Monte Carlo integration is really when it comes to doing higher dimensional integrals, because it scales with space much better than quadrature rules. But we're going to stick in the univariate case just for our example today. Okay, so let's look at a quick Python example of how we could implement some form of Monte Carlo integrator in Python. Okay, so here we have a notebook that you'll be able to find underneath this video. And what we'll do is we'll just quickly walk through how we can use Monte Carlo integration. So we'll begin by just performing our import statements of numpy and matplotlib to visualize some of the results. Okay, and then we have our definition over the Monte Carlo integrator that we just introduced a moment ago. So what we actually need to do is we need to define a Monte Carlo integrator, which we can Okay, so what we need to do is define our Monte Carlo integrator. So this function takes in a function which defines the thing that we're going to integrate. It takes in a lower limit, takes in an upper limit, and then we define a sample size. But of course that can be changed when we pass this parameter to the function. Okay, so the first step is generate samples on the uniform distribution between A and B. So one way that we could do this is we could say samples is equal to np, and then so NumPy has this built-in random number generator or pseudo random number generator which we can use. So we can access that with random.random, and then we pass in the number of random samples that we like to generate. Okay, but the problem with that is that that defines our random variables on the interval 0 to 1. And so what we need to do is transform these samples such that they lie in the interval A to B. So one way we can do that is we can simply add the lower limit. So lower limit, add, and then what we're going to do is just scale the size of the samples. So previously it was 0 to 1. We want that to be between A to B, so we can just do upper limit minus lower limit, and then we can just times that by the samples. Okay, so we now have our SI here. This is our samples drawn from our uniform distribution on the interval A to B. So the next step is to evaluate the function. So we can do that by simply saying, let's say, f samples. So this is all of the samples that come back from the function, and we can just say function of transformed samples. Okay, and then finally what we need to do is find the sample average and also multiply by A minus B. So let's say approx, because this is our approximation to the integral, we can do upper limit minus lower limit . Divided by the sample size. So that's this part here, and then all we need to do is multiply that by the sum of all our function evaluations. So we'll take this and place it here, and then we're going to return approx. So if we just run that, and then to test out our implementation, what we can do is we can come down here and we'll just run a quick example. So we're going to define the function sin x, so we do that here, and then we can call our function Monte Carlo integrator. We pass in the function and the limits, so 0 to pi, and we expect that we should get 2 out. We use 1,000 samples, so let's evaluate that. Okay, so we get 1.975. What happens if we increase the number of samples? We keep on getting closer and closer to the true value. And of course, the more samples we use, the longer it will take to evaluate, but we keep on getting closer and closer to evaluating the true to converging to the true value. Okay, well, what about if we use something a little bit more complicated? Well, let's say we want to integrate x squared sine cubed from 0 to pi. So here we have the Wolfram alpha, which is evaluated at 4 us, but we can let's try evaluating that with our function. So we can come back into here, we can say x squared times by sine, and then that was sine cubed, and it's also on the integral 0 to pi. So yeah, x squared sine cubed on the integral 0 to pi, and we run our 3.666. The true answer is 3.61. Okay, so of course we're introducing this idea of Monte Carlo error because it's an approximation technique, but as we keep on increasing the number of samples, we'll get closer and closer to our true to the true value of the expectation, and hence the true value of the integral. Okay, so the final thing that would perhaps be good to look at with this is the idea of what is actually going on with Monte Carlo integration. And so what I've done is I've implemented the same function again, but this time I've included a plotting function, which will allow us to sort of see how samples are being drawn, and hopefully this will give us an idea of what's going on. So there we go. So if I pull over the window here, what happens is it's drawing samples from this interval of 0 to pi, and then it evaluates the function at these samples that we keep on drawing. And then, of course, we're multiplying by the width of 0 to pi, and so really what all of these lines represent is a box of associated area. And what we do is we add all these areas together and we divide by the number of areas that we've had. Okay, and then that is our estimate of the total area underneath this curve. Okay, so that brings us to the end of today's talk. As I said, this notebook will be available underneath the video, so feel free to have a go at that. And I hope you enjoyed today's seminar. And next week we're going to talk about random walk metropolis Hastings. Thank you.